Well, we're back, folks. We're in the middle of Chapter 3. We're only probably going to do the first 3 sections, so this is the middle. We've talked a little bit about the basics of probability, and now we're going to talk about 2 other things, conditional probability and the multiplication rule. Heads up, the multiplication rule is really easy. One small condition on it, excuse the pun. Conditional probability is a little bit trickier, but if you think about it for a while and try some exercises, you'll catch on really easily. All right, so we talked about the basic concepts. We'll talk about the multiplication rule and conditional probability. And the next time we'll talk about the addition rule, which isn't too much different from the multiplication rule, but the big thing to remember about the multiplication rule is that the key word here is the word and. And the key word for the addition rule is or. So keep that in mind. That'll help you keep things in perspective and get you on the right path. So here are some things we're going to do. Remember what I've suggested in the past. Don't be afraid to pause. I don't mind that at all, because I'm not doing it live. I'm alive, but I'm not doing it live. All right, so we'll start with the conditional probability, and this is how it goes. We're talking about the probability of an event, but not just the probability of an event. We also have some prior knowledge that something else has already happened. And that's what this means. The probability of an event occurring, that's E, given that something else has already happened. And we've got some good examples coming up too. This is the notation for it. The probability that B happens, that's our focus. And this is the information we've already got. A has already happened. What's the probability of B if we already have the information that A has already happened? Here's an example, and I think you'll probably get the idea now. It says 2 cards are taken in sequence, that's one after another, from a standard deck, and that's 52 cards. If you're halfway familiar with cards, you'll know what I'm talking about. You want to find out the probability that the second card is a queen. So that's your focus. And the information you've been given in advance is the first card was a king. And you're going to assume that king was not put back in the deck. Now because of that, because the first card is a king and not replaced, the remaining deck has 51 cards. In other words, one's gone. We didn't put it back. So we can ignore that king. At that point, there's only 3 kings and 51 cards in total. Now there are still 4 queens. So our probability before, because there are 4 kings possible to pull out, but only 51 cards left. And use the calculator a little bit, and there's our probability. Here's another way of looking at things, depending on what the situation is. This one shows the results of a survey. We surveyed 970 U.S. adults, because we're interested in all U.S. adults as our population. But we've got a sample of 970. You want the probability that an adult is 18 to 64 if we pick someone at random, but we already know that the adult has ridden as a passenger in a self-driving vehicle. Now, how do we work this? Well, first of all, we already know that the adult has ridden in a self-driving vehicle. So we're only talking about these numbers. We can forget about that. those are the people that have never driven or ridden in a self-driving vehicle. So these are the only people that we're considering. Where's my cursor again? These are the only people we're actually considering. Now we want to know how many of them, or what probability is that we'll get an 18 to 64-year-old. Well, here we go. The probability of this event, I'm going to take the easy route, is we've got 202 possible 18 to 64-year-olds, 202, and we've got a total of 225. There's our probability. All we have to do is do the arithmetic, and there's our probability. Remember, we had a condition on it that says we're only looking at the ones in this column, and we want to know what's the probability of getting someone who's 18 to 64 years old. Next, independent events. This is when the other event does not change the probability of the one we're interested in. Something's happened, but we don't really care because the probability of our event is not changing. And it looks a bit like this. The probability of B, that's our point of interest, given that A has already happened. And if they're independent, then we don't care about what happened to A because the probability doesn't change. Or if you look at it from the other point, if B has already happened, that doesn't change the probability of A, it's still probability of A. And the nice thing is, if it's not independent, it's dependent. That makes sense, right? We're going to check and see whether the event is independent or dependent. Now what we're going to do is we're going to select a king from a standard deck. So this happens first. We don't replace it. Then we select a queen from the deck. So how does that work? Well, if we pick the queen, given we already picked a king, and remember we've got 4 queens, but the king wasn't replaced. We've only got 51 cards. Now how does that change things? Well, if we had started at the beginning and just chosen a queen, our chances are there are 4 queens, 52 cards. Notice the probability has changed. So these are dependent events. So those are our 2 results. The probability actually has changed because that first card was taken out. So they're dependent events. Now we're going to try it again. We toss a coin and we get a head. And then we're rolling a 6-sided die and getting a 6. So what's the probability of getting a 6 if you've already gotten a head with tossing the coin? Well, does it make a difference whether we get a 6 or not after we flip a coin and get a heads? Not really, because the coin has nothing to do with rolling the die. And one more, just to get you thinking a little bit more about this. What about these? Driving over 85 miles per hour and getting in a car accident. Are those independent or dependent? If you're driving over 85 miles per hour, does that change your chances of having a car accident? Well, yes. Going that fast, you are more likely to be in an accident. So, they're independent event or dependent events. Now the multiplication rule. Now this says we're talking about two events, A and B, talking in generic terms, and they're happening one after the other. So we're saying the probability of A and, notice the and, B, is the probability of A given the probability of B given that you already had A. And what do we have? Since that probability does not change, just because A occurred doesn't change the probability of B. If they're independent, then to get the probability of A and B, remember and, we just multiply the two individual probabilities. All right, let's try an example to solidify that information. We're going to pick two cards, and we're going to put the first card back. Without replacing the first card. Find the probability of selecting a king and then selecting a queen. Let's see. The probability of selecting a king is right here. Since we've got a fresh deck, it's 4/52. The probability of selecting a queen, if we've already selected a king, well, there's one less card in there. We've still got 4 queens, as we did before, but this time we've only got 51 cards to choose from. And that's our probability. One event in this sequence with the other, one after the other. Next, let's take a look at a coin and a die again. The probability of tossing a head and then a 6. They're independent because they don't have anything to do with each other. So just multiply the individual probabilities. Oops, here we go. There's the probability of heads and the 6. 1/2 for the heads, 1/6 for rolling a 6. And there's our probability. Just multiply them since they're independent. Now let's get a little bit more serious. We're talking about a surgery. Unfortunately, some of us have problems with our ACL at some point. One of my students a few years ago came in one day and she was on crutches, and I said, "What's wrong?" Well, she had torn her ACL, which took her out for an entire season. Anyway, back to the point. The probability that the surgery is successful, we're going to say, is 0.95. 95% of the time the surgery is successful. Now we want the probability that 3 ACL surgeries are successful some morning. So how do you do that? Well, they're independent, so all we need to do is multiply those 3 probabilities. And of course, those probabilities are independent, so they're all the same. And there's our probability at the bottom. A little bit over 85% chance that all 3 are going to be good. Let's take another twist on that. Find the probability that none of them are successful. Well, take note that this is the opposite of having all of them be successful. In a way, but not totally. What's the probability that you have an unsuccessful operation? Well, success you have a probability of 9.5. So what's the probability for the failure? Well, it's the complement, which is 0.05. None of them are successful means you have a failure, and then a failure, and then a failure. So it's 0.05 times 0.05 times 0.05. And let me clear this out because it's going to be messy in a second. Okay, there we go. Multiply those three probabilities, and the good news is the probability that none of those surgeries is successful is 1/10,000. So out of 10,000 surgeries, 10,000 mornings of doing 3 surgeries, only 1 out of 10,000 times are all 3 failures. Okay, one more. We're still with the ACL surgeries, but this time we want the probability that at least one is successful. Okay, this is a problem because we would have to take the probability that one is successful plus the probability that 2 are successful plus the probability that 3 are successful. Ooh, that doesn't sound good at all. We'll have to do 3 problems and add them together. No. There's another way of doing that. Because at least one is the opposite of none are successful. There we go. The opposite of none are successful. Now what we already found was that none are successful has a probability of 0.0001. Since this is the opposite, then we'll take 1 minus 0.0001, and that'll be our probability that at least one was successful. And do the arithmetic, and there's the chance that at least one is successful tomorrow morning. All right, let's talk about medical school for a moment. We've got 19,326 medical school seniors. So they're ready to be doctors. So I'll get to their residency at least. Of these seniors, 18,108 were matched with residency positions. And 75.6 got one of their top 3 choices. I'm sure they're dancing in the streets if that happens. Medical students rank the residency in their order of preference, and program directors rank the students. A match means the student's preference list and the program director's preference match. So they get a placement of the position in a residency position. So what's the probability that a randomly selected senior was matched with a residency position and it was one of the senior's top choices? Now you might want to check back here again. Remember, you can use pause, but we'll sneak back here anyway. You might want to get those. You had 19,326 seniors and you had 18,108 matched with residency positions. When they get the residency positions, 75.6 and get one of their top 3 choices. So what do we have? Matched to residency position. We already figured that out or had the numbers. You can see that's the 18,108 divided by all the medical students. And doing that, we get also this probability. Given that this happened, that's the A that we see right here. Given that that happened, what's the chance that they got one of their top 3 choices? That's what this says. So, all you need to do is multiply those two together. Our first one times the second one, and our probability of a randomly selected senior was matched with residency position and they got one of their top 3 choices. Multiply those two probabilities, these two, and there's our probability right there. How about this way? Find the probability that a randomly selected senior was matched to a residency position and did not get matched with one of their top 3 choices. So, we're going to change the second part to this. Now this is they're not matched with one of their 3 choices, but they did get a residency. So how do we do that? 1 minus the top 3 choices, that's 0.244. Now, would it be unusual for a randomly selected senior to be matched with a residency position and it was one of the senior's top 3 choices? It's not unusual because it happens about 70% of the time. That means it happens all the time. Well, that's it, folks. That is section 3.2, and you learned about conditional probabilities and the multiplication rule. Next time, we'll take the addition rule and talk about that. Remember, the multiplication rule, the word you want to remember, the word you want to remember is the word and. And that gives you the multiplication rule. Next time, we'll talk about the addition rule, where we'll be talking about statements with or in them. Until then, you take care, and we'll see you soon.